Yeah. Yeah. So last time we talked about isomorphism theorem. Yeah. So let's see how what does that mean for us in this context. Yeah. So say phi is a linear operator on a vector space V, finite dimensional vector space V. Let's say. Yeah. And K is the kernel of phi, so it's a subspace of V, and W is the image of phi. Yeah. So first of all, is K direct sum W isomorphic to V? So how many of you think this is true? How many of you think it's false? So what does isomorphism theorem tell us in terms of phi? What do we know? What does the first isomorphism theorem tell us? Yeah, tell me what does the first isomorphism theorem tell us?
V mod kernel is isomorphic to image.
Yeah. So for the kernel, so in this context, it tells us that V mod K is isomorphic to W, right? So maybe by first isomorphism theorem, we know that V mod K is isomorphic to W. Yeah. So if we think of so this tells us that V is isomorphic to W direct sum K if we think of it as external direct sum. Yeah. External direct sum. So this statement is correct if you are thinking of it as an external direct sum. K is a vector space, W is a vector space. You can take the external direct sum. Yeah. So K plus W is a direct sum. But if we think so here anyway, so think of it as external direct sum. Yeah. Meaning you don't think of them as subspace of V, but some vector space in their own right, and then take the direct sum, right? But what if we try to think of them as subspace of V? Yeah, so if you have two subspaces of V, then you can ask whether V is a internal direct sum of K plus W. So is the second statement true? So what does this mean? If this is the internal direct sum, what does this equality mean?
Every vector in V.
Yeah.
Every vector in V can be represented as the sum of an element in the kernel and an element in the image.
Uniquely, yeah.
Yes.
That is so. In other words, K plus W is equal to V, and K intersection W is 0. Yeah. Or any vector in V can be written as a element as sum of an element in K and an element of W unique. You know, there are no choices involved. So is this true? What do you think? If I take a linear operator V, then is this true? So how many of you think it's true? How many of you think is false? Yeah. So it has to be either true or false. Yeah. So you have to raise your hand in one situation. Yeah. So make a guess. How many of you think is true? No, no. And how many of you think is false? Now you're just guessing. Yeah. So you can sort of say intuitively what you feel. Should it be true?
No.
No. Yes. No one wants to guess. So this may not be in general true. Yeah. So can you give an example where this is not true? So you'll have to give me a linear map such that this doesn't happen. Yeah. In other words, you have to make sure that k intersection w is not zero. Yeah. So can what would be such a linear map? So I don't know. I don't have an example written down, but one can try to make it. Yeah. So one can try to do 2 by 2 matrix such that the image is maybe a subspace generated by E1. Yeah. And the kernel is also subspace generated by E1. Right. So maybe you'll have to put 1 here, 0 here. This certainly kills E1. Yeah. But its image is, and I don't want it to be non-singular, right? So this will maybe not work. One has to do something more, something smarter. So it kills E1, but its image is not E1, yeah? So maybe one has to go to a higher yeah, so let's try to do something like that. So A, B, C, D. Then you have to look at its image, and kernel shouldn't be. So the image and kernel shouldn't become linearly, and it should be a. So maybe one has to go one step higher.
Sir,
Yeah.
can we think of a map like this, wherein E1 is mapped to E2
Mm-hmm.
and E2 is mapped to 0
E1 is mapped to E2.
and E2 is mapped to 0?
Yeah, and E2 is mapped. This is what we want. Yeah, then the image is E2 and the kernel is also E2. Yeah. So let's
Yes.
try to get a linear map like this. Yeah. Yeah, maybe this is a better way. So E1 is mapped to E2. So 1, 0 should go to 0, 1. Yeah. So it should be. So this was 0, 1, and yeah, so okay, so we'll have to solve some equation, but this will do. Yeah, so we can find such a map. So let's try to solve. So E1 goes to 0, E1 goes to E2. Yeah, so phi of E1 is E2, so it's 0, 1. This is how we should write it. Yeah, and phi of E2 is 0, so 0, 0. So this should do. Yeah. So if you consider a linear map to be this, given by this matrix, then the image of A is 0. Yeah, so this is okay. Yeah, so image of A is spanned by E2. Yeah, and kernel of A is also spanned by E2. Yeah, so W, which is W, and K is also this.
So how is this image W here?
So A times XY, if you consider, what do you get? It is 0 times X, yeah, 0 comma X, 0X, right? So if you multiply the first column, first row, you get 0. And if you multiply the second, you get X, right? Which of course is X times E2. Okay. Is this fine?
So how do we get K plus W equal to B here?
No, we don't get. So what we are trying to say is that this is not possible. Yeah. So we are trying to disprove that this is an internal direction. Right. So I mean, it can't. So this internal direction precisely means that K plus W is equal to V. So if V happens to be equal to this, then this, in fact, only one of the two conditions will ensure that this happens. Yeah, because of the dimension count. So if K plus W is V, then K intersection W has to be 0. Yeah, because dimension of K plus dimension of W is dimension of V. That is from first isomorphism theorem. Yeah. So if K plus W is V, then K direct sum W is also V. It is an internal. Or if K intersection W is 0, then also you can conclude that K direct sum W is V. Yeah. So in fact, in this case, these two statements are these three statements are equivalent. Okay. So this is not true. So in fact, what you can say is that K plus W is equal to V if and only if K plus W equals V, if and only if K intersection W is equal to 0. Yeah. So there are three equivalent. These are three equivalent conditions. So you only have to check one of them. Yeah. So so this by first isomorphism. So this follows from the first isomorphism theorem. Dimension V is equal to dimension K plus dimension W. Yeah. So so if K plus W is whole of V, that means the intersection cannot be bigger. Yeah. So that dimension kernel, so that rank nullity formula we had, from there it will follow. So we had this formula, right? If you have two subspaces of V, W1 and W2, then dimension of V1 plus V2, the dimension of W1 plus W2 is same as dimension of V plus dimension of W1 intersection W2. So this now all the equivalence follow from if this statement which we proved long time ago, subspaces from the rank nullity modulus or extending the basis kind of argument. Yeah, dimension of V plus dimension of W1 intersection W2. Yeah, maybe extending the basis is dimension of W1 plus dimension of 2. So from this you get that W1, I mean So use this and the isomer and this equality to prove all these three equivalences. Okay. Is this fine?
Yes.
Okay. So there is a subtle difference between when you can argue. Yeah. So you'll have to check some things that K intersection W is indeed 0. Okay. Okay. So now let's start this discussion on orthogonal matrices. Yeah. So we'll talk about orthogonal matrices, but first let's talk about orthogonal vectors. Yeah. So in Rn, if you take two vectors x and y, so this you may have seen in R3, for instance, in either in math or physics courses, that you can say that two vectors are orthogonal if their dot product is 0, where dot product x dot y is defined this way, summation xi yi. Yeah. Or in matrix notation is just x transpose y. If you think of x and y as column vectors, it's just x transpose y. Yeah. So this is called the dot product, or at least in your high school is called the dot product. So in R2 we have a formula for the dot product, if you recall. Yeah. So the dot product of 2 is just the magnitude, the length of the two vectors times cosine theta, where theta is the angle between the two vectors. Right. So you remember this from your high school. Yeah. If you are given two vectors in R2 and you want to know what is its dot product, then you look at so this comes from parallelogram law, if you like. Yeah. So the dot product is basically the length of this guy, and then you can use trigonometry to show that it is the length is same as the length of this vector, length of this vector times cosine of this. Okay. So what is an orthogonal matrix, or what is an orthogonal transformation? So it's like so we will give a precise definition, but it's like changing the coordinate axis. Yeah. So we want so this is like x-axis and this is y-axis. So we want to change the coordinate axis. So in the sense that these two vectors, so there are too many x's and y's. Yeah. So let's just get rid of. So we want to change the coordinate axis such that the angle between the two vectors don't change. Yeah, and the length of the vectors don't change. So we are just trying to sort of, or in other words, we are rotating the vectors, both the vectors by the same angle and so on. Yeah, so that is roughly, or you can flip it. Yeah, so roughly these are the rotation. So in R2, it is either rotation or you can take the reflection. Yeah. So once we define orthogonal matrices, orthogonal transformation, we'll see these are the only orthogonal transformations of R2. Okay. Once we define more precisely. So let's define it. Yeah. So first let's say what are orthogonal vectors. So two vectors so we can do this over any field. I mean, R is not necessary. So to define things, we can do it over any field. Yeah. So let x and y be in Fn, F a field. And so two vectors x and y are called orthogonal, and is written x perpendicular y if the dot product is 0. Right? If x dot y, their dot product is 0. So this is again like from the physics. Yeah. So are you guys familiar with this thing, dot product from physics? Yeah.
Yes, sir.
Okay. So now this is the definition of two when you say two vectors are orthogonal. Yeah. Now if you are given a subset S of Fn, and I want to say that this subset is orthogonal. So we say that a subset S in Fn is called orthogonal if I take any two distinct vectors, they should be orthogonal. Yeah. So it's called orthogonal if for all VW in S, V not equal to W, they should be orthogonal. Okay. And a basis of Fn, which is also orthogonal set, is called an orthogonal basis. Okay. So these are the three things we want to define. So this is orthogonal set. So called an orthogonal set and orthogonal basis, and there are pair of vectors being orthogonal. Okay. That's fine. So orthogonal basis just means an orthogonal set which is also a basis. Okay. The first observation is that if you take an orthogonal set in S, then it's automatically linearly independent. Okay. So in particular, this tells you. So if you know this, then in particular, what it means is that in particular, an orthogonal generating set of V is an orthogonal basis, right? Because it's automatically linearly independent and it generates. So hence it's a basis. Yeah. But why is an orthogonal set linearly independent? So you check it directly, yeah. So you I mean, so suppose suppose you want to say that an orthogonal set is linearly independent. So suppose summation ai vi I equals 1 to n is 0, where vi's are in S, yeah, and AIs are in F. Then you want to say that each of these AIs are 0. So what do? So you did take a dot product with each of these VI, yeah. So let's say V equals LHS, yeah, or maybe let's do it in one go, yeah. So VI dot product summation AI VI, yeah. So this dot product, of course, so this dot product, of course, behaves linearly in the second variable. Yeah, so you can sort of, or it's doing vi transpose. So whatever way you want to see it, this is just summation. So too many i's. Yeah, so let's call it vj. Yeah, I equals 1 to n. So this is same as I equals 1 to n. AI vj dot vi. Yeah, this dot product. But it's an orthogonal. S is an orthogonal set. Yeah. So this is going to be 0 unless I is equal to j. Yeah. So this is aj vj dot vj, right? And remember, it's yeah. So maybe one should yeah s. Yeah, so I don't want orthogonal set to contain 0. Yeah, a subset S of non-zero elements. Because if it is 0, then it's a problem. Yeah. So since Vj is non-zero, we know that the dot product of Vj with itself is positive, is non-zero. Yeah, if it's in real number, then it's actually positive. But otherwise, you can't say it's positive, but at least non-zero you can say. Yeah. So that tells you that. Yeah. So let me just. Yeah. So this is true. I don't know. Yeah. So if in Rn, let's just state it for Rn. Otherwise, I don't know. Yeah. So Rn and So we'll work only with Rn. Yeah, so let's not. So definition you can make it, but otherwise I don't know whether the self dot product is zero or not, is positive, is non-zero or not. Yeah, so it may be non-zero, but when you are doing over R, it is okay. It's positive, that we know. Yeah, so this is this. So I mean, we are taking a dot product with zero. So this start with is zero. This implies Aj is zero, since Vj dot Vj is not equal to zero. Yeah, it's in fact positive. Greater than. Is that okay?
So why did we change it to Rn? Won't it hold for any Fn? Because your Vj dot Vj is actually just norm Vj, which is
Vj dot Vj for general field, I don't know if it is going to be non-zero. Yeah, so for some complex numbers, it may become something, or some finite fields, etc. It may become zero. Yeah. So for instance, you can look at F2. Yeah. So over F2, 1, 1 is the dot product with itself is zero. So for positive characteristic, you can already see this is not true. But even for complex numbers, it's not very clear. Yeah, so I don't think it is true, even for complex number. You can try to cook up some example. Yeah. So you need Rn in this case. Is that okay?
Yes, sir.
Yeah. So at least for finite field, you can see this is not true. So you need some hypothesis. But even in complex number, I think you can cook up example. Okay, so let me just write this more clearly, because Vj dot Vj is positive. Okay, so if you have an orthogonal set in Rn, then it is automatically linearly independent, and hence if it generates, then it is a basis. Yeah. Now slightly different definition. So orthogonal is okay, but sometimes we need. So you look at standard basis, for instance. So they are orthogonal, but their norm is also one. Yeah. So such basis is called orthonormal basis. Yeah. So S is called an orthonormal set if S is orthogonal, and the norm of every element in this is automatically one. Okay. Is that fine? So that is what an orthonormal set is, and similarly, orthonormal basis maybe one set. An orthonormal basis is a basis which is an orthonormal set. Which is also an orthonormal set. Okay. Any questions or comments? Okay. So n cross n. So now we will define what an orthogonal matrix is. Yeah. So n cross n matrix is called orthogonal matrix if A transpose A is one, is identity matrix. Yeah. So let's see some examples now before discussing more. Yeah. So this is the definition of orthogonal matrix. So what's an example of an orthogonal matrix? Any example? Identity matrix. Yeah. So identity, of course, identity transpose identity is just I square, which is I. Yeah. So that is one example. But can you give some other examples? So maybe a 2 by 2 matrix.
Zero, one, one, zero.
0, 1, 1. So if you, so if you square it, you do, so it is already symmetric, right? So A transpose is A. So this is another example, maybe let's call it 2. Then A transpose A is the square of A essentially, which is identity. Yeah. Okay. Any other example of orthogonal matrix in 2 by 2?
Diagonal matrix.
Say that again. Diagonal matrix. What should be the diagonal entry? Maybe -1, yeah. That may work, yeah. So this is, but nothing else will. If you are doing it over real numbers, nothing else will work, or complex numbers or anything, yeah. Because you want A transpose A to be identity, yeah. So whatever A entry you put, A square must be 1. So there are two solutions, 1 and -1, right? So what else? Can you think of something else other than these? So these are sort of maybe first and third is certainly obvious. 2 is the only non-trivial example we have got. Can you think of some other non-trivial example? So I gave you a hint in initial. So I told you orthogonal matrices are like orthogonal transformations are like rotations. Yeah. So orthogonal matrix should be sort of rotations and reflections and so on. So from there, can you say what should it be? Yeah. 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 So you can do cosine theta, and maybe minus sine theta, sine theta. No? So this is sort of rotation by angle theta or minus theta, depending upon. So this is probably by angle theta. Yeah, rotation by angle theta. So so now you can check whether it is rotation or not, but you can obviously check, right? A transpose A, what do you get? So so what is A transpose? A transpose is cosine theta minus sine theta, cosine theta. Yeah, this is how A transpose looks like. So A transpose A is cosine square theta plus sine square theta. Yeah, and then this becomes 0, this becomes 0, and then this is also cosine square theta plus sine square theta. So as you can see, this is again identity. Yeah. So at least these are certainly orthogonal matrices. Yeah. So we will see that these are more or less the all of them, in the sense that you'll have to change a little bit. Multiply these two matrices. What do you get? This 2 and 4. So then you get something. So what do you get? So these will give you all the orthogonal matrices. Yeah. So it's either reflection or rotation and combinations of these. Of course, product of product of two orthogonal matrix is also orthogonal. Yeah. A, B orthogonal. I hope this is true. Yeah. So then A times B transpose AB is what? So B transpose A transpose A B, which is so A transpose A is identity. Yeah. So you get B transpose B, which is again identity. So you can see that set of orthogonal matrices form is closed under multiplication. So it's actually closed under so it's under multiplication it forms a group. It has identity. It is closed under multiplication. Yeah. So it's a subgroup of invertible matrices, and it's yeah. So it forms a group. Yeah, so it looks complex. I mean, in R2, for instance, we used rotation to figure out what are all the orthogonal matrices. So in general, it looks a little. So to characterize it is a bit um, complicated, but we'll see some easy characterization. Yeah, so sometimes some in other terms, in terms of orthonormal basis and so on. Yeah, so the first proposition is that a matrix, given a n cross n matrix, it is orthogonal if and only if the columns of A form an orthonormal basis of Fn. Yeah, or another characterization is that you multiply A by, so you consider A times X and A times Y. The distance, so the dot product doesn't change. So dot product of AX dot AY is same as dot product of X and Y for all X and Y. Then also A will be orthogonal. Yeah. But before proving that, let me make this definition for a linear map. So this is orthogonal matrices. Linear map phi from V to V is called orthogonal if phi x dot phi y equals x dot y for all x, y in. Yeah. So, or in other words, so if we had proved this proposition, this would mean that the matrix of phi with respect to some basis must be a orthogonal matrix. Yeah, because phi x is same as ax. Yeah, with respect to that basis and so on. Okay. So let's see a proof of this proposition. So this is not difficult. Yeah, proof of proposition. This is more or less straightforward. It's just analyzing what it means. So one implies two. So we are given A is orthogonal matrix. Yeah. So A transpose A is identity. Yeah. But this precisely means that if I consider this matrix as a first column, yeah. So I'm writing it like this: A star to the A is like this, yeah. So so A is a n cross n matrix. It has these columns, which I can think of it as A star 1, A star 2, A star n. Yeah. Then so A transpose A equals identity implies that so how do you compute do the matrix multiplication? The first row of first row of A transpose you multiply by the first column of A. But what is the first row of A transpose? A transpose looks like A star 1 transpose. Yeah, so not because it has to be a row matrix, right? So A star to transpose and so on. So if I do the transpose of A, this is how it will look like, right? So A transpose A is just multiplying these things and getting, and what we get is identity. So not this doesn't imply anything. A transpose is A is this, then A transpose is this, and then this. So maybe I can write these two statements together with the fact that A transpose A equals identity means that A star 1 transpose A star 1 is 1, or more generally, maybe let me just write it. A star I J is the ijth entry of the identity matrix, which is delta ij. Yeah. So that tells you that is this okay? This statement?
Yes, sir.
Yeah. So that tells you that A star 1 to A star n, they are orthogonal, right? Because I mean, if you take I different from j, they're pairing. This is the dot product, as we agreed. Yeah, this is the dot product of these two. So this is an orthonormal basis. Normal basis. Okay, so that completes the proof of one implies two. Yeah. Similarly, you can prove two implies one. So what does two implies one say? Yeah, so maybe two implies one, two implies three, and then maybe we'll do three implies one. Okay. So yeah, two implies three. So let's say columns of A, columns of A form an orthonormal basis of Fn. Yeah. Then we want to show that Ax dot Ay is same as actually, let's prove one. I mean, two and one are more or less equivalent. So let's prove two is equivalent to one, and then maybe one and three are closer. So maybe we'll prove one and three are. Okay. Let's see. So three implies three and one are also equivalent. So yeah, let's just do two implies one, and then we will do three is equivalent to one. Yeah. So of course this is also easy, right? So if since A star 1 to A star n are orthonormal basis, normal basis, then A transpose A, we know the ijth entry of A transpose A is going to be A star I transpose A star j. Yeah. Which is precisely delta ij. Yeah. Hence, because of the orthogonality condition. Yeah. So this the dot product is precisely A star I transpose A star j, and hence this tells you that A transpose A is silent. Yeah. So this is because A star 1 to A star n is an orthonormal basis. Dot product, we can write it this way. Yeah, that is the point in terms of matrix multiplication. Okay, so this what we have proved is 1 is equivalent to 2, and then for 1 equivalent to 3, maybe again maybe at one go. So what does one says that A transpose A is identity. So 1 implies is equivalent to saying that A transpose A is identity. Yeah. And so and 3 says that yeah. So now if you have, okay, so maybe I'll have to yeah. So this implies that X transpose A transpose A Y is equal to X transpose Y. Yeah. But this is equivalent to saying this is equivalent to saying AX transpose AY is equal to X transpose Y. But this is same as the dot product. Yeah. AX dot AY is equal to X dot. Yeah. So this proves I guess 1 implies 3. For 3 implies 1, we'll just have to reverse this thing. Yeah. So this holds for all. So for all xy in for all xy. So to reverse this, all you have to check is that suppose this holds for all all xy, then how do you prove that A transpose A is identity? So you can just put, I mean, since this holds for all xy, in particular, it holds for E1, E2, and so on. Yeah, standard basis. So now, so X transpose A transpose AY is equal to X transpose Y for all xy in Fn, so not F, but Fn. Then take xi x to be ei and y to be ej and y to be ej. Then what do you get? Ei transpose A transpose A ej is delta ij, right? But what is E? So this is same as saying AEI transpose AEJ is delta ij. But what is AEI? A times EI is precisely the ith column of A, right? If you multiply A by the standard vector EI, then you'll get the ith column of A. And similarly, the jth column of it. So this is A star I, A star J, not comma, but dot. A star J is delta ij for all ij between 1 and n. Yeah. So this tells us that so yeah, so I guess we have proved this implies so this implies 2. Yeah. So what we have proved is 3 implies 2. So I guess what we have proved is maybe 1 implies 3 here, and this proves that so this is 3 implies 2. Yeah. So the columns of A form an orthonormal basis. So I guess we have done everything. 1 implies 3, 3 implies 2, and 2 implies 1. Yeah. So maybe 1 implies 2 was not needed. So we could have gotten rid of 1 implies 2. Okay. Is that fine, everyone? Any questions or comments? Okay, so this is how you can find orthogonal matrices in general. Yeah, so if you can find an orthonormal basis, then that guarantees then you can use it to cook up orthogonal matrices and so on. Okay, good. So now let's try to study them in more precisely. Yeah. So so maybe before so I wanted to do R3, but before that, let's finish the R2 picture. Yeah. So we already saw that these rotations and these reflections are orthogonal. Yeah. Now let's try to show that these are all the orthogonal matrices in 2x2 matrices over R2. Yeah. So let's finish that, and then we will go towards so 2x2 orthogonal matrices over R. Yeah. So what does it mean? So we have so say A looks like so a matrix, orthogonal matrix, or any matrix for that matter, looks like this: A, B, C, D. And since it is orthogonal, we want to impose that condition and see what values we can get for A, B, and C, D. Yeah. So A transpose will look like what? So A, B, C, D. Yeah. And then we want A transpose A to be identity. Yeah. So A transpose A is what is A transpose A? A square plus C square, right? And yeah, so let me know if I make some mistake. AB plus CD, yeah. And then again AB, is it AB plus CD again? Yeah, AB plus CD. And it should be a symmetric matrix because A transpose A is a symmetric matrix. You transpose, you get same thing. And then C square, B square plus D square. Yeah. So this should be identity. Yeah. So that what does that tell us? That A square plus C square must be 1, and B square plus D square must be 1. Yeah. And AB plus CD is equal to 0, and and that's it. Yeah. These are the three identities we get. So from here, we have to conclude that it has to look like one of these, right? So yeah, so or in other words, AC and BD should be orthogonal vectors, and their norm should be 1. So any vector, so AC is a vector in R2, and its length is 1, right? So if you think about it, you take any vector in R2 whose length is 1, then any vector looks like cosine. So if this is the vector AC, then you can think of it as angle theta and length 1. Yeah. So if the length is 1 and this angle is theta, this vector is cosine theta, comma sine theta. Yeah, where theta is this angle. No matter which vector you take, theta could be any angle between 0 and 2 pi, less than 2. And if you want some sort of uniqueness, you say strictly less than 2 pi. Yeah, So A must be something like cosine theta, and C must be sine theta. Yeah, A and C. Right. So this is how the columns of A must be an orthonormal basis. So, this is how you can think of. So now. Um, and we don't, so you can make sure A and C are this, but B and D, then you have to satisfy B and D are some other things, but you'll have to make sure that this yeah, so then B and D are yeah, so what do you get? So um, so B and D are also of that kind, but we also want this AC should be orthogonal to BD. Then what should we do? Yeah, so AB plus CD is 0. So to make sure of that, AB plus AB equals minus CD. Yeah. So and so that tells you that A over C is minus D over B. Yeah. So A over C is or maybe C over A. Let's just write in terms of tangent theta. C over A is same as B over D. Yeah. Just trying to. So you get that this implies that tangent theta is minus B over D. Yeah. So that tells you that what does that tell you? So it doesn't uniquely determine it. Yeah. So there are only two possibilities. So see B. So where what you can say is that this BD is B is some cosine alpha, and D is some no, you can't say that, but okay, so uh, oh, sine over, so yeah, this is okay. Sine over C over A is minus B over D. Yeah. So and B square plus D square is equal to 1. So that tells you that um, so B over D is what you get is minus tangent theta, tangent of minus theta or something. Yeah. Minus tangent theta is tangent of minus theta. So and B and D are of norm 1. So that tells you that B must be, I'm not making any mistake, right? So B must be minus sine theta, sine. So let's see if these possibilities are right. Yeah. So it could be sine theta, and D is minus cosine theta. This is one possibility, or B is minus sine theta, and D is cosine theta. These are the two possibilities, right? These are the only two possibilities. There is no other. If you take some other angle, then it will not work, right? So these are the only two possibilities. Is that okay? So the two matrices possible are so if you take this cosine theta, so without loss of generality, we can assume that it looks like so sine theta minus cosine theta, or you can, so these are the possibilities. So I hope this will take care of all the things. Yeah. So cosine theta, sine theta, and minus sine theta, cosine theta. Yeah. So remember this was all rotations. Yeah. So we saw that rotations are certainly, we want to show that everything is either a rotation or a reflection times rotation. Yeah. So let's just multiply this by, so consider cosine theta minus sine theta, cosine theta times that reflection 0, 0, 1, 0. Yeah. So for instance, if you take theta to be pi over 2 in this formula, if you take theta to be pi over 2, you will get 1, no 1, 0. So if you multiply these two, what do you get? You're getting something silly. You get minus sine theta. But I want to say that these two together gives you all the, I mean, this matrix plus this matrix gives you everything. Yeah, so maybe one has to conjugate it, then it will be okay. This has determinant -1, yeah, so let's just do this. Yeah, so yeah, this will, yeah, so let's look at this product. So what do you get? So this is post there you'll get sine theta. So if I'm making some mistake, let me know. Yeah, and then cosine theta. I'm doing the multiplication of the first two terms first. So cosine theta and minus sine theta. It's this, and at times 0, 1, 1, 0, and you get cosine theta and sine theta and minus sine theta and cosine theta. Okay, which is precisely cosine theta. This is cosine of, so you can put minus theta here, yeah? Sine minus theta, sine with negative sign here now, sine minus theta. So it is the matrix of that form. That is what I want to say, cosine minus theta. Yeah. So if I conjugate by this thing, then we get rotation by minus theta instead of plus theta. Yeah. So So what I'm trying to say is that this guy, if you do is also sort of generated by these two matrices. Yeah. So rotation and flip gives you all the possible. So all the possibilities are in this collection for various thetas. And I'm just trying to tell you is that rotation and flip gives you everything. Okay. So if I had done it more geometrically, it would have been more nice. So this is by angle, changing the angle by theta. So you and then you flip, and again, so first you flip, then change the angle by theta, and then flip back. Then you get this transformation. And this guy, yeah. So you'll have to change by minus theta instead of theta. No, this is not what, so this is not right. Yeah. So I want to get, I want to get this particular matrix, and I'm not getting that matrix. So something is wrong. So why am I not getting this matrix? This is this you get back one of the rotation matrix. So this is not what I wanted. I mean, the calculation is right, but this is not what we want to show that cosine theta, sine theta minus cosine theta is also a product of a matrix like this and the reflections. Yeah. So how do we do that? No, so sorry. So this is I've written this as the reflection, but this is not a reflection. This is also a rotation. So that was the problem. Sorry. So see what is this matrix 0, 1, 1, 0? This is not a sorry. So maybe let's just erase this. This first, I mean, this is the calculation is okay, but let's just try to understand what is this matrix. 0, 1, 1, 0. This is sort of isn't that reflection?
So the first one is reflection.
0, 1, 1, 0 is also a reflection, right?
Yes.
It is a reflection. So these two should generate. This and this together should generate. But there is another reflection. Yeah. 1 minus 1, 0, 0. Yeah. So this is reflecting along. So this is a reflection along some other axis, some more complicated axis. This is the reflection along x-axis. Y becomes minus y. Yeah. So I mean, both are reflections, but this is reflection along x-axis. So it will send x comma y to x comma minus y. Yeah. So it's a reflection along along y-axis. So if you multiply these two, then you will get you'll certainly get this. Yeah. So there is no issue with it. So you can do you should be able to obtain by these two as well, but maybe you'll have to do a little more work. So maybe you can try this. So I don't know, it's not coming out automatically, but at least I've shown that rotation plus one reflection gives you everything. Yeah. So instead of don't use this, use this reflection. But any reflection will work. Yeah. So even this should work. This is also a reflection. It's a reflection along x equals y line. Yeah, so it's a more complicated. X axis becomes y axis becomes x axis. So it's a more complicated reflection. So that's why when you multiply these two, it becomes a bit more complicated. But it's these two together should generate everything as well. So that maybe you can try to work it out as an exercise. Yeah, but this is also a reflection along x-axis, and this reflection together with this gives you this. Yeah. So that so every orthogonal matrix in of over R2 is generated by rotation and a reflection. Yeah. So that that completes our argument for R2. Any questions before we move to R3? Yeah. So it will come out. Just that you have to struggle a little bit. Maybe. You multiply these two and maybe change the angle a little bit, and it should come in this form. So, okay. So cosine theta, sine theta is sine pi by 2 minus theta is cosine theta. Yeah. So maybe that kind of transformation you'll have to do to get to the other part. So you'll have to use this identity. Is sine theta and so on. So if you use this kind of identity, so though you got in the diagonals, you are getting some sine theta and so on. So if you do that this identity, it will be in terms of cosine then with some other angle. Okay. So try that and it will work out. Any questions or comments before I go to R3? Okay, so before going to R3, let me make some definition. Yeah. So about rigid motion. So in R3, if you take a ball in R3, yeah, and you sort of rotate the ball and so on, then it's a rigid. I mean, you're not allowed to bend the ball and stuff. Yeah, so that is called a rigid motion. Yeah, so we'll make it more. Make a definition and make it more concrete. What I'm trying to talk about. What happened? Why did I come into here? Something like that. Yeah. So definition: a rigid motion or an isometry is a map M from Rn to Rn. So definition is for any dimension, but we will think of it and will apply it in R3 such that it preserves distances. Yeah, such that it preserves the distance between any 2 points. Yeah, so it preserves distances. In other words, mx, the distance between mx and my, yeah, is same as the distance between x and y. So I don't know if you want to write it like norm, it's okay. So either way, so this is the distance between mx and my in Rn shouldn't change. Should be same as the distance between x and y. So such a motion is called a rigid motion or an isometry. Okay. So, I mean, orthogonal matrices are like sort of like rigid motion. Okay. So maybe proposition. So this is similar to the matrix one which I wrote. So let M from, as long as so of course translation is also a rigid motion, so you have to fix 0. Yeah. So let R M from Rn to Rn be a function. Then in fact you can sort of characterize as orthogonal matrices if you think in the right way. M is a rigid motion. So that means it preserves distances, which fixes origin. Yeah, so you are not allowed to do translation. Because remember, translation will also fix distances between 2 points. So you're not allowed, because we want linear maps. Yeah, so linear maps doesn't allow translation. It fixes it. 2 mx, the inner product between mx and my is same as the inner product between x and y. Yeah. And 3 m is a linear map. So see, we have not even assumed any, we haven't assumed anything more or less, right? Not even continuity for this thing. Yeah, and it forces it to be a linear map given by multiplication by an orthogonal matrix. Right? So let's see why this is true. Okay. So proof. So this looks very, very sort of strong. Should have moved it. Yeah. Okay, I'll do that later. So so maybe one implies 2. Let's try to prove 1 implies 2. So what does 1 say? It is a rigid motion and it fixes origin. Yeah. So rigid motion means we have to find the dot. So we know that mx minus my, this distance, times x minus y sorry, mx is same as distance between x and y. Yeah. So if we write it in terms of dot product, what you'll get is that this dot product is same as x minus y dot product x minus y. Yeah. So if the distances are same, these dot products agree. But what is this? What is left hand side? If you expand it, then this is the length of x, yeah, plus the length of y, minus 2 times the dot product of mx dot my on the left hand side, and the right hand side is same. You just drop x and y. Yeah. So that tells you length of x plus squares. Yeah. Length of y minus 2 times x dot y. Right. But remember, length of mx and length of x must be same. Yeah, because you can. I mean, m fixes 0. So mx so mx minus m0 length is same as length of x, x minus 0, which is length of x, right? And m0 is 0, so this tells us that length of mx is same as length of x, right? So this note, so this maybe is a note. So this note implies that I can cancel out since m0, so this is because m0 is 0. Let me pause a bit, yeah. Yeah, so from here we get that mx dot my. So this mx square and x square you can cancel out, my square and y square you can cancel out, and minus 2's you can cancel out to get that mx dot my is same as x dot y. Yeah. So this proves 2. Okay. So and now for 3, I have to prove that it is a linear map, and we want to prove that it's given by an orthogonal matrix. Yeah. So let's try to prove 2 implies 3, and then we will prove 3 implies 1. 3 implies 1 is straightforward because we already saw that orthogonal matrix is going to preserve distances. Yeah, so that part in fact we know that the inner product we already saw 3 implies 2, for instance, in here. Yeah, so if you have an orthogonal matrix, ax dot ay is same as x dot y. So in particular, it will preserve lengths. If it preserves inner product, then it will certainly preserve distances between any points, and it will fix the origin. Origin because it's linear map. So we only have to do 2 implies 3, and then 3 implies 1 is obvious. So let's just try to do 2 implies 3. Okay. So we have M is a map from Rn to Rn such that this mx, the inner product is preserved. From there, we want to show that it's an orthogonal matrix. Yeah. So so sort of I guess similar sort of proof. So what you do is I'll have to make a matrix. Yeah. So yeah, so we will look at where the standard bases go, and that will give us the matrix in some sense. Yeah. So you look at ME1. Yeah. So ME1 is going to be a vector in Rn. Yeah. So let's call that vector A star 1. Yeah. Or more generally, MEI, call it A star I between 1 and n. So EI is standard basis. Okay. So or rather it should be written differently. Yeah. A star I is ME1. That is the right way to, ME1 EI is already known. We are trying to define A star I. You define it as MEI. Yeah. So so we got columns of so A is now just A star 1. So it's a matrix whose first column is A star 1, second column is A star 2, and so on. A star n. Yeah. So so by 2, we know that the distance between M ME1 EI MEJ is same as EI dot EJ, yeah, which is same as delta IJ, right? So that this tells you that A star I dot A star J is equal to delta IJ, right? Which tells you that the columns of A are orthonormal. So that tells you that A is orthogonal matrix. So by 2, we already know that A is orthogonal matrix. All we have to check is that M and A are more or less the same, defines the same function. Yeah. So claim mx equals A times x for all x in Rn. Yeah, this is what we'll have to prove. So if you prove this, then we are done, right? We wanted to show that M is given by a multiplication by an orthogonal matrix, right? So this is now straightforward because you know what is x? A typical vector there, x is let's say x1. So this is how it looks like, yeah? X is some vector in Rn, it's given by this. But this we can write it as x1 E1 up to xn En. Yeah, this is what it looks like, right? So, um, um, so, so Ax, what does Ax looks like? It looks like, so A is linear at least. So this tells you that it is x1 A E1 plus xn A En. But what is A E1? A E1 is the first column of A, right? And first column of A was declared to be ME1, right? So this is x1 times ME1 plus xn times MEN, yeah? But M we don't know is a linear map. So I can't say this is M of x1 E1 plus xn En. So we'll have to argue differently to say that uh, um, this is same as mx, yeah? So but we know that it preserves inner product, right? So what do we know about mx dot me1? This is same as x dot e1. Yeah, it preserves because it preserves inner product, which is which is x dot e1 is just x1, right? So that tells you that so we'll have to use some so yeah, so I want to say that mx is same as ax, yeah? So we want to say that this distance between these two is 0, yeah? So let's just try to calculate the distance between these two. So, okay. Yeah, so so if I want to prove this is the zero matrix, I have to just this is the zero vector. I just have to compute that the distance is this. I mean the length of this is 0. Yeah, so which is same as saying that this inner product is 0. Yeah. So what is this inner product? So,
Sir,
yes.
Can we substitute for x1, etc., xn in ax?
x1, etc.
X into m of e1. I mean, dot product m of e1. Then we have m of e1.
So maybe one has to do something like that. Yeah, one thing we know. Okay, sorry. So maybe what we can do is by the previous line, at least if I do the dot product with me1. Okay, let's do this. Yeah. What do we get? So mx dot me1 is x1, and ax dot me1 is so this is x1 minus ax dot me1. Yeah, and this is again this is 0, right? Because ax dot so this is ax dot sorry, maybe for matrices we know it is okay. Yeah, so that is the point I'm trying to use. Yeah, so this is x1 and minus ax dot ae1. But this also preserves, since A is orthogonal, this is same as x dot e1. So it's x1 minus x1, which is 0. Yeah. So mx dot minus ax dot me1 is 0. But this is true. I mean, I can do this with any EI, not just E1. Yeah. Similarly, mx minus ax dot mei is 0 for all I between 1 and n. Yeah. So that means you are, but what is this? So if I want to write this in terms of matrix notation, these n equations, then this is same as saying you are taking the dot product with so this is A times mx minus ax. Mx minus ax is some vector, and you multiply by A. Yeah. A or A transpose. Yeah, so it doesn't matter one out. I think it's A. Okay. So you get that this is 0. Yeah. So this these n vectors, if you think about it, so these equations, these n equations you get, if you write it in matrix notation, you get that this is 0. Yeah. But A is an orthogonal matrix. Yeah. So that tells you that mx minus ax is 0. Yeah. You can pre-multiply by A transpose if you like. Or A is invertible, whatever way you want to use, you can. Hence, mx equals.
Sir,
Yes.
can't we directly say that mx is equal to x from the fact that mx minus ax dot product m of ei is equal to 0 for all I?
Yeah. So you can say it directly by, I don't know, it's orthogonal to it is going to be orthogonal to a basis vector. Yeah. So that is how you can think of it as 0. A vector which is orthogonal to a basis vector has to be 0. I mean, otherwise you will get a orthogonal set of bigger length, yeah, bigger than the basis, which is not possible. So either that or computationally, either way, you get that mx is equal to x. So this proves 2 implies 3, and finally 3 implies 1. is okay. Yeah. So from the previous proposition, as soon as you have a linear map, so we proved that if you have an orthogonal map, then is orthogonal, then it preserves distances. Yeah. So 3 implies 2, for instance, or 3 implies 1 also. So it is going to preserve origin, and it preserves inner product, so it preserves distances as well. Yeah. So that is 3 implies 1. So this completes the proof for this thing. Yeah. So we couldn't come to R3, so we will do, I mean, it's almost time, so we'll do R3 next time. Yeah. So let's stop here, but we'll continue this discussion next time.